Sankaranarayanan. And the first time we met was during indeed my first visit to India. It was in '87, and Shankar was a kid at that time, and I was very happy that he took time to introduce me to Mumbai and all the mysteries of Mumbai. And so now let us back to real business. And so please, Shankar, we are going to talk about the distribution of the restricted sequence of integers 2 to the little omega of n. Thank you very much. Please.
Okay, thank you very much for the kind invitation and my best wishes to the birthday babies Srini and Kalyan. Yeah. So today what I am going to talk about is, this is a work jointly done with my student, Mr. Venkata Reddy. This has already appeared recently, actually, 9th December. It has come out, the paper has come out. Okay, some motivation, maybe motivation I can skip because are specialists. So, well, maybe if you define the Mobius function mu1 to be 1 when n is equal to 1, minus 1 power k when n is product of distinct k prime factors, 0 otherwise, then of course one knows that the bound of this command in absolute value less than or equal to some constant times x power half plus epsilon, this is equivalent to Riemann hypothesis. One knows that. So generally, when you have a good arithmetic function and when you are interested to study about the summand with the weight gn, then because left hand side is a discontinuous function, all that you can expect is either an upper bound or an asymptotic formula depending on the situation. So naturally one has more leverage if you know the generating function attached to the coefficient gn, namely the L function Lg to be summation n is equal to 1 to infinity gn over n power s. And if you know more analytic properties, very nice properties, then of course you can expect more information about this summand. So one of the important problems in number theory is the divisor problem, namely the summation n less than or equal to x dn, the problem considered by Dirichlet, which has such a main term and error term, of course. Error term, probably the best result as of today known is something like ex less than x power 131 divided by 416 plus epsilon due to actually, and one knows that such omega result holds good for this error term, and I think this result has been improved by Hafner to this. So you can see that there is a long gap here for various arithmetic functions people are interested. So in this lecture I just want to mention that if you consider the function 2 power omega n, where omega n is the number of distinct prime factors of n, of course you know that this function 2 power omega n is multiplicative, and in the literature of course one knows that summation n less than or equal to x 2 power omega n is satisfying certain asymptotic formula with the main term, and the error term is somewhat like O of x power 1 over 2 plus epsilon. I am not x power epsilon, I am not saying very clearly, I mean you have more refined estimates in the literature. What we are interested in this work is that instead of the summand runs over all the integers, if we restrict to our sparse sequence of integers, what will happen? So our aim here is to see the following. Namely, we define the function f1 as f1 is equal to 1 and f1 to be 2 power omega n if n is powerful, 0 otherwise. So that you can easily see f1 is multiplicative here, and if you see the L function attached to this arithmetic function is nothing but this guy, and because it is multiplicative by Euler product representation, one has such an Euler product, which is absolutely convergent in the half plane real part of S is bigger than 1 over 2. And of course, naturally, you expect the Riemann zeta function and other factors come into the picture here. And of course, here life is somewhat rather difficult, more difficult than usual 2 power omega n. 2 power omega n case, if you take that L function attached to those coefficients, is nothing but zeta square s divided by zeta 2s or something. But here you need a little more information. That's what we do here. In the case of Riemann zeta function, of course, you have a functional equation of this kind, and this chi is the conversion factor which behaves in absolute value as mod t power 1 over 2 minus sigma in any fixed vertical strip for large T. So, let me just recall the Riemann hypothesis, which tells you that all the non-trivial zeros of the Riemann zeta function, they lie on the critical line, real part of S equal to 1 over 2, and we call the strong Riemann hypothesis. The stronger version is that all the non-trivial zeros of the Riemann zeta function lie on the critical line, and each such zero is simple. As of today, whatever the computation results known for a larger height, they support the strong Riemann hypothesis. This is just not a proof, this is just an evidence, that is all. Okay. So, one knows some zero-free region for the Riemann zeta function due to Vinogradov. Later works, of course, some kind of improvement on the constants and so had been done. So, what we show here is that in the sparse case, that means that we are considering this summation n less than or x, Fn, in the case Fn, which is defined F1 is equal to 1, Fn is equal to 2 power omega n when n is square full, 0 otherwise. For this summand, we show that this has such a main term, and the error term is going to be something like x power 1/4 and some small increasing function. This is what you prove. Of course, this result is unconditional, and I should also mention that from the generating function, when you investigate, it is not too difficult to find out. Of course, there are some certain standard methods which one can refer to, a paper of Balasubramanian and Ramachandra, I think, which appeared in 1980s in JNT, I believe, from which one knows that this error term, for example, one can show it is something like omega x power 1 over 8, I believe. Yeah. So still there is a long gap. So, the second question is there a way here to improve this? So, to improve this, of course, life becomes very difficult. So, what we do is that we assume strong Riemann hypothesis. Okay, you assume strong Riemann hypothesis. Can you say something much better? Indeed, I can say something more. That's what the second theorem tells you. Second theorem, in fact, when you assume strong Riemann hypothesis, namely all the non-trivial zeros of zeta ls for L is equal to 2, 3, 14. Of course, for all these Riemann zeta function, if I assume the strong Riemann hypothesis, then of course I can show that this sum has some extra main terms. One more main term is there. Yes. And then I can show that the error is something like O of x power 5 over 22 plus epsilon. One can see 5 over 22 is strictly less than 1/4. So that improves, of course, with you have taken out some main terms involving the zeros of the Riemann zeta function. Effectively. Yeah, so the proof, let me just sketch the proof. Just before, let me say, whatever. Yeah, so some lemmas. So I have such an Euler product representation in the half plane real part of S bigger than 1 over 2. So let me just recall yeah, whenever you have fn is 0, whenever p square doesn't divide n, etc. So you decompose this L function to the following. This lemma 1 is somewhat crucial. Let me tell you, I think I need a clear picture at least up to this level, namely real part of s is bigger than 1 over 15. So until then I have to do, then only I can prove theorem 2, at least by this argument of this article. Okay. So how does one achieve this continuation? So what we do is write x is equal to p power minus is in the Euler product, and of course you as long as real part of s is bigger than 1 over 2, you observe mod x less than 1. So to prove this particular expression, you first observe 1 plus 2x square plus 2x cube, etc. into product of polynomials in the form 1 minus x power m or its inverses from m is equal to 2 to 14, possibly with some error terms. This is what we do. Of course, for a fewer product terms with mind manipulation one can do. When you want longer thing, of course we use Mathematica to confirm everything. Okay, so you have such a representation. So you can observe that this infinite sum is the product of these two. Then you adjust one by one, etc. with an error of x power 15. That's what is happening. So that of course I don't go into. So finally you put x is equal to p power minus s, which will lead to your f of s is nothing but this quotient of these zeta functions times h1s, where h1s is converges absolutely and uniformly in the half plane real part of s is bigger than 1 over 15. This is what I want for proving theorem 2. So the next lemma is of course the Sankaranarayanan version of lemma 1, which is first a few factors I have taken, and h2s I am just writing this way. So so one observes that in the half plane real part of s bigger than 1 over 15, the function f of s has singularities taking the poles at the points 1 over 2, 1 over 3, 1 over 7, 1 over 8, 1 over 12, 1 over 13, 1 over 14, as well as at the non-trivial zeros of zeta 4s, zeta 5s, zeta 6s, which appear in the denominator of that product. Of course, one knows that because I am assuming strong Riemann hypothesis, namely the zeros of the Riemann zeta function lie on the critical line, as well as they are simple for various L is equal to 2 to 14. So I can explicitly compute the residues at is equal to 1 over 2, 1 over 3, 1 over 7, 1 over 8, 1 over 12, and at these points 1 over 8 plus I gamma 1 over 8, 1 over 10 plus I gamma 1 over 10, 1 over 12 plus I gamma 1 over 12. All this of course with certain orders are there, so you just compute the residues, then apply Cauchy residue theorem, find out the estimates for the left vertical line contribution and horizontal line contribution. Of course you need to use certain mean value estimates, maybe functional equation and so on, and try to see how much one can tighten the belt here. So yeah, so some details are given. Yeah, and next lemma what I use is the fourth movement of the Riemann zeta function, which is well known to everybody, and this is of course a result of a bit of and then another result, an important result which tells you the Riemann hypothesis, which implies that for every sigma between half and 1 for large t, the Riemann zeta function as well as 1 over the Riemann, of course here sigma is strictly bigger than half for this. It should be O of mod t power epsilon, if you assume Riemann equals. So I will use all this along with functional equation also. So once you have all this, I start with the Parent's formula. So this is the sum. The line you start with the 1 over 2 plus 1 over log x, and you have such an error estimated from the tail portion. Then you move the line of integration to 1 over 4 minus the constant over log t power 2/3 double log t power 1/3. I just for simplicity write gt to be the junk. Then you apply the Cauchy's residue theorem, and one notices that for the first theorem, unconditioned result, I use lemma 2. F of s has two poles, one at s equal to 1 over 2 of order 2, another at s equal to 1 over 3 of order 2. That gives you essentially the main terms of this type. Then these are the errors coming from the horizontal and vertical line contributions. This is the tail portion. So if you estimate the left vertical line contribution in absolute value, precisely maybe you use functional equation and so on, and then you just you observe that the contribution is nothing but x power 1/4 minus c by gt, some extra factor, small factor. Yeah, and the horizontal line portions I2 and I3 in total, they contribute to this much. Then here, of course, I have to use the functional equation, and then you estimate explicitly what happens here. So what I see here is that as long as my t is bigger than x power 1/4, this is the estimate comes into the picture. These two are the dominant error terms. Now you have to choose t. We choose t such a way that these two are of similar order. That tells you exactly this is the error term what we try. This is unconditional. Of course, the second theorem is somewhat more interesting, though it is conditional. It gives some light. Of course, lemma 1, that's what I told. That has some crucial, computation effectively. So in this case, first of all, you start with the line of integration here 1 over 2 plus 1 over log x. The tail portion error you have. This itself tells you that error time improvement is possible only when t is bigger than x power c star, with c star is strictly 1/4, bigger than 1/4. That tells clearly. So provided by some means, if you can extract a few more main terms somehow, that's what we do by assuming the strong Riemann hypothesis. So you move the line of integration to real part of s is 1 over 14 plus 1 over double log x, and then you see poles from s equal to 1 over 2 of order 2, 1 over 3 of order 2, 1 over 7 of order 2, 1 over 8 of order 4, 1 over 12 of order 5, and so on. And simple pole, because of your assumption strong Riemann equation, a simple pole at each s is equal to 1 over 8 plus I gamma 1 over 8, a pole of order 2 at each s at 1 over 10 I gamma 1 over 10, a pole of order 3 at each s 1 over 12 plus I gamma 1 over 12. They come from these factors which appear at the denominator. Yeah, with modulus gamma 1 over 2, modulus gamma 1 over 10, modulus gamma 1 over 12. It's strictly less than t, up to height t, you have to count. So when you do all this, anyway residues you have computed, you just fit in all these things. So precisely you have J1, J2, J3, this residue and this error. So the left vertical line contribution, again you do it on this line 1 over 14 plus 1 over double log x, use the functional equation and fourth power mean of the whatever. So it tells you that the estimate is going to be something like x power 1 over 14 plus 1 over double log x, t power 4 by 7 plus 22 by double r is plus some 52 epsilon naught part of epsilon is any small positive constant. And the horizontal line contribution, of course, just to see more clearly, what we do is split this interval into a few parts, like 1/14 to 1/12, 1/12 to 1/9, etc., etc. Then you can see more clearly, and you can use wherever necessary functional equation of the Riemann step function, conversion factor, growth. You have to take it into account. All this, if you do, it tells you that all these things are controlled in absolute value by these expressions. Of course, you know that in any of these maximums, you can see that these functions as a function of sigma, this is monotonic in that interval. So maxima appears on the extremities. So take the left bound and right bound for each interval, and totally that will tell you these are the estimates what you get. Precisely this estimate is going to dominate over all other things as long as t is bigger than x power 1/4. Once you observe that fact, you can see that the residues coming from these guys, they are all going to be small in any case. So these three main terms will be there, and then these two terms are going to be there. Yeah. Now my job is to choose t. I choose t such that these two are of same order. So what we do is here, t is something like x power 3 by 11, which is strictly bigger than x power 1/4. That does your job, and that gives you precisely what you want, with of course these three extra main terms, with error is of x power 5/12 plus epsilon, 5/22 plus epsilon, which is much better. Of course, you have three summed main terms, whatever. But the whole point here is that one observes here, for instance, the S1 sum. If you take this is the sum, my t is something like x power 3 by 11. That's my choice. So trivially, if you take the absolute value inside and so on, this is going to be some maximum of these constants, and x power 35 by 88. That is much worse. Similarly, trivial bounds are much worse. On the other hand, what one observes here is that because of the oscillatory factor x power I gamma business, you expect enough cancellations to happen, but we are not in a position to prove anything on the line of cancellation. Thus, we are tempted to make the conjecture that these three summands S1, S2, S3 are of order of x power 5/22 plus epsilon on the safe side, though we are not in a position to prove anything on this point. I think I am through. Yeah.
Good. Thank you very much. Well, are there questions? Yes, please.
Yeah.
So I have two questions, if I may ask.
Please.
So this x to the power 1/4, the length of the interval. I mean, how are you getting x to the power 1/4? Is it
Which
possible to push below?
Which one?
So if you, in your proof, this t length you are taking as x to the power 1/4, right? T is greater than x to the power 1/4. I think in both the theorem you are using that.
No. Just to see.
Yeah. So
Just to see, these are all smaller. If you put t is at least x power 1/4, these are all smaller, so I can omit.
yeah. So what I'm saying is it possible to have a, I mean, do you expect to have a more finer estimate so that for smaller length also?
Okay, let me tell you. Yes, I can understand what you want to say. See, the thing is, maybe you can continue in a better region. You can have more factors. It may improve a little bit more, but with more main terms you should be able to take out. That is also there. But even the improvement will be at third or fourth decimal. This is what I expect. But more main terms will come into the picture. Only under the assumption of strong Riemann hypothesis still. Yes? Yes. Unconditionally we don't claim anything here. Yeah? Under SRH.
Yeah. I have another question.
Yes, please.
Could you please go back to theorem 2 statement?
Theorem
2.
2.
Yes, so next question.
Statement yes. Yes.
So is it possible to say something about the constant of the lower order term, like C3, C4, particularly sign?
I don't have any idea. These are some real constants C1, C2, C3, C4. But D1 gamma, D2 gamma may be complex constant. Yes?
Okay. Thank you, sir.
Yeah.
Nice talk. Thank you for the nice talk.
Thanks.
Is there any special form for this error term, like Voronoi or some kind of exponential sum to work with?
Maybe, we don't know. Should work out. Yes, I don't know. Maybe.
But is it expected to have such a thing?
Maybe. Because usually, you see, of course here sparse sequence you are doing it. Usually if you take 2 power omega n for all n, it behaves like a divisor function. I mean, it agrees with the divisor function when n is a prime. Yes. That much only you can say, nothing more. Yes. Yeah.
Yeah.
I have a question. So, is there anything better that you can do if you consider smoothened sums? Like you add a compactly supported function and you take summation f of n, let's say phi of n by x, and
You should try.
then you will get a better handle on the other terms, and maybe, I don't know.
You can try.
Okay, and just since we're on this slide of theorem 2, the exponent of x, right? It's like x to the 1/12 is the smallest main term that you have. I think it's on the next page.
Yes, yeah.
But your error term is like x to the 5/22.
Hello,
So,
boss. That is why I told you x power I gamma is there.
okay.
That is the oscillatory terms. So there may be cancellation. We don't know.
So you expect this, whatever the sums, to be also big O of 5.
Small.
To
We
be-
expect
okay.
to be small.
Okay, but
But-
you have this precise version.
But we don't know how to prove.
Okay, okay. Thank you.
Okay. I would like to raise a question.
Yes.
So you start with the divisor function,
Yes.
and then you mention the function which is in some way the strong multiplicative function associated to the divisor function, which is 2 to the omega of n,
Yes.
which doesn't depend on the prime powers.
Yes.
But you are summing them over square full number and not over all the numbers.
It's
Why?
sparse sequence. When you restrict the summand, what is the behavior?
Yeah, but what about the divisor function then over this set?
Very difficult.
Okay.